In my first video, linked below, I carried out testing of the stock blades of the helicopter, measuring the thrust and the torque, and then comparing that against my blade element momentum theory results. However, they weren't as I expected. So I pulled the helicopter bits and I noticed the spindle that spans between the two blade grips looked a bit bent. So I wasn't too sure what that was, so I put it all to bits and tried to measure the spindle. So the flattest plate I have in my workshop is actually the base plate of my Prusa printer, and I had a metal ruler. I rolled the spindle around it, trying to look for some gaps, but there was just nothing noticeable. So I determined it was okay. However, I had a metal head lying around, so I spent an evening and put the metal head on the helicopter to hope that this would fix all my problems that I've been seeing in regards to pitch and obviously looking bent, and basically everything would just be much nicer. Now this metal head was super fiddly to put together and put on. It has like M2, M1 screws. It was quite pain, little bearings in the rotor grips, but all in all, as you can see, it came out looking pretty sweet and it flies just as well. And then put the helicopter back on my test rig after remeasuring the pitch of the blades, which I must admit was a lot better with the full metal head. And I ran through a series of testing again, measuring different throttle points, pitch settings, where I get thrust and the force from torque, which I can then compare against my code and analysis. So here you can see I am measuring the RPM of the motor as I go, using that laser tachometer and a reflector on the outrunner of the brushless motor. I actually had a lot of trouble with this. It wasn't the best RPM measurement, and I do need something better going forward. The thrust results, when compared against the analytical prediction, actually came in really good. I was pretty stoked with this. We're within about 10% of predicted, which I think is probably as good as I can get for the setup with my RPM and pitch measurement as it was. So I was really happy with this on these stock standard blades. I don't think, yeah, it's perfect. However, the torque measurements were quite a way off. We're talking about 20% on some of them. I think there was something wrong here with my measurements. Something wasn't quite right, so I need to get back on the test stand and retest this. But in the meantime, I wanted to get into printing a blade for this, and that's where we begin. So I jumped into Onshape for this. As I said before, it's great for doing odds and ends of CAD. I started off with a solid design, and I tried a lot to get the tip right. With this design, it worked out okay, but as you can see, I've just got a couple of small fillets. I then, really wasn't happy with this, so I switched to a surface design, and I could really shape that tip much better with the surface design rather than solids and using fillets. Surfacing is much better for this, and it's really easy to use. If you haven't tried surfacing, you should really do it. A combination of surfacing and solids to get you some good looking parts. I then iterated a bit on the surface model, and I got it looking somewhat pretty good. However, I decided it wasn't really working out for me, so I switched back to a solid I'd done some test prints and the tip just didn't really come out. So for all that work in CAD, it just really wasn't shown on the printer. So I switched back to a solid, which was easy to model. I just added some basic fillets to the tip. And this came out in CAD good enough. And to be honest, on the printed part, I have to do a little bit of sanding. So it doesn't matter that it's not perfect, especially on the Prusa Mark III. So I ended up leaving the blade like this. And I also ended up tidying up the trailing edge to print it better with the nozzle diameter and the resolution of the printer. So this came out pretty well. And now I had some NACA 0012 blades ready to go. They came in at 3 grams and that's what I predicted they to be, which is perfect. I needed to make sure that the blades would actually not rip themselves out of the blade grip. So I just did a simple shear analysis at my expected rotational speed. So the mass and blade center mass I got from Onshape. I was then able to calculate the centrifugal force acting on the bolt, the blade. And then knowing the root thickness and my blade diameter, the whole diameter, I was able to work out the shear stress at the root of the blade. My main concern is the blade shearing out of the bolt. I don't think the bolt would ever fail. So with PETG in factor of safety 1.5, you can see I have a pretty large margin of safety on the root. So I only carried out this analysis on the blade itself, as the metal grips I expect to be good, or otherwise I wouldn't sell them. I did this with PLA, ABS, and a bunch of other materials, and to be honest, they all came out with a high factor of safety and a high margin of safety. I then threw these on the Prusa and printed them in 3 different orientations: flat, 45 degrees, and 90 degrees. 90 degrees being up on the leading edge. I tried with a 0.4 nozzle and a 0.25 nozzle, and what I found was there was not much difference between the 0.25 and 0.4 besides some extra detail. For the time it took to print, the 0.4 was much better. And after some sanding, they came out reasonably good. So I was happy with that. I then printed a bunch of the NACA 0012 blades. As you can see here, this is how they come off the printer. They're a bit stringy. I didn't dry the PETG enough, but they look pretty rough when they come off the printer, but with a bit of sandpaper, they come out looking pretty good. So I was pretty happy with this lot. As I said, some light sanding, and these blades come out looking pretty good, as you can see here. I was pretty happy. They have quite some strength. The airfoil came out really nice. I then proceeded to also give them a bit of a clear coat to help protect them, and it gives them a bit of a shine. And the hope is the clear coat also fills some of the gaps from the printing. So all in all, a pretty good, strong blade. I then ran my Python code for the 0012 airfoil to give me some baseline points for further testing. As with all my testing, I ran through a bunch of different pitch points where I measured the RPM, thrust, and the force from torque. However, my results were not as expected, as can be seen here. What I found is that the lower pitch settings, the predicted versus measured thrust was quite a way off. However, as the pitch setting got higher, especially test 6.2, this was within 10%, which is what I predicted. The same went with the torque setting. The higher pitch setting, the closer to the analytical results I got. I looked at the airfoil, and as you can see, in the first graph in the top left, the optimal lift coefficient to drag coefficient ratio is actually at about 5 degrees of pitch. So my highest pitch setting was 4.5 degrees. So this is pretty close to the optimum operating point for this blade at my particular Reynolds number. If we look at the second graph, you can see the blade stalls at about just after 8 degrees. So the line up to that stall point, the lift coefficient line, is pretty linear and it's pretty stable. And as I said, I was at 4.5 degrees. So I think I had some good results from X-foil to use there. However, below 3 degrees, as you can see, we have a different slope and the points are a bit less. So maybe this had something to do with my analysis and my predictions not being right at this lower pitch number. So this is something I need to look into. Also had a lot of trouble with the RPM on these tests. This laser tachometer is not really working out that great. If you took notice in the tests, upon shutdown, the helicopter seemed to have a lot of flex and the rotor disc didn't seem to be level. So I think the skids attached to the mounting frame just wasn't working out. So I jumped into OnShape and I branched off from the old design to a new design. And the new design basically picks up on the skid attachment points with some M2 bolts that slide into the holes. And then we have the battery holder that sits out front. Everything picks up on the same main bearing and the helicopter just sits on top. So here's the helicopter on the new stand. So this is the old one, attached to the skids. The new one, I pull the skids off and I use some M2 screws and we go straight through the skid attachment point and we move the battery out here. This should work a lot better. The idea is just to put some rubber bands around here and strip it over top. It's not producing a lot of thrust, so it's not going to matter with rubber bands. Plus also there's quite some friction on this. So this should give some better results. So now I need to retest the 3D printed NACA 0012 blades with the new test setup at the high pitch angles and just confirm that everything is a-okay. And then if that all works out, my next test will be to take the same blade profile but then add some twist to it. So twisting blades basically improves the efficiency, so I should get a higher figure of merit and less power and be able to fly longer.